Hello. In this particular video, we'll be basically elaborating on different code conversion techniques. In our syllabus, we have code conversion from BCD to ASCII, ASCII to BCD, decimal to hexa, hexa to decimal, number systems. And we can, the same logic, knowing the logic, mathematical model, how to convert from one system of numbers to another, we can directly incorporate that particular model in terms of a program. I'm taking an example of converting a BCD number to ASCII. Whenever I write a BCD number, whenever I say BCD number, it is basically keys, number keys that I press to enter. For an example, when I want to enter a BCD number 10, I will enter 1 and then I followed by 0. So there are keys. So if you observe the first two columns of this particular picture, we are having keys from 0 to 9 to give rise to any number of combinations, BCD combinations. In that particular combination, we are converting it into hexa or ASCII. What is ASCII? It is basically a standard of communication used. Whenever I press 0 while I communicate, it is 30 that is going through the communication medium. Similarly, when I press 2, it is 32, 3, 33, so on till 9, it is going it as 39. So we need to convert this into a standard. Taking an example here, I'll go to the Keel software. Okay, let me take an example. When I press the BCD number, say 65, you can note I had pressed two keys. First was 6, the other one was 5. So the ASCII equivalent of this is, for the first key it is 36, for the second key it is 35. If you compare closely these two results with what my original data was, we basically have 6 separately taken, added 30, 5 is also separately taken, added with 30. And the numbers are separately displayed. How can we do it? So I'll take 65, my original number. I'll add it with 0f. When I add it with 0f, anything added with 0 is 0. Anything added with 1 is the same number. Anything added with f, that is 1111, I'll be getting back same number. So if I add 65 with 0f, I will be getting 05. The same way, whenever I add 65 with f0, I will be getting 60. But I want 06. So what will I do? I will swap the number again. So once I swap, I get 06. Now we have 05 and 06. These are keys separately pressed. So what I can do, when I have 05, I'll add 30 to it. When I have 06, I'll add 30 to it. So do we get 36 and 35? Yes. This is the logic that I have written here in the form of program. I am assuming an internal memory location 50 where I basically enter the number that I want to convert it into ASCII. So in that particular location, I am fetching the data, whatever number you had stored, I am fetching that number here. And I am also copying it into R2 because I want 65 two times, right? So temporarily I am making the copy of that number into R2 also. I am adding that number with F. Okay, so I will get 0f. Right? Now, I will OR it. ORing is nothing but again equivalent of arithmetic operation addition. So I am ORing it. Why am I doing it? I want to keep it completely logical. I don't want to mix an arithmetic and logic functions into the same program. So I am keeping it in terms of OR. So I have ORed it and copied to accumulator. I am saving it in the next location. Taking back the original number which we had backed up in R2, I am swapping it, ANDing it, ORing with 30. So again the number is converted back to ASCII equivalent. So now let's see the result. I'll delete this because that is my logic. So let us retain only the program part. So I'll save the program. I've done all the prerequisite steps of creating projects, selecting hardware, typing the program and saving it as .asm since we already know the procedure. So I just save the file. The file is already added. Let me directly translate and check if I have error. If there are no errors, the file will be automatically transferred to a binary format. Good, we don't have any errors. So for the file is transferred to binary. Next, I am going for build. Later, I'll just go for debug. Very simple. So we want to see in the memory. Since we are using internal memory, it is D:. From the program, we know the address is 50. Just press enter. Give the number. Let me give 65, same number. Again, it is left to you. You can give whatever number you want to convert it into ASCII. Let me run the program and see the result. Yes, 65, lower byte, lower nibble first, 35. Higher nibble next, that is 36, installed. Let us check with the other number too, just out of curiosity, whether it is working fine. In 30, let me give 28. I am running, right? 3 plus 8, 38. I mean 30 plus 8, 38. 30 plus 2, 32. It's working fine. So when you go for a conversion of BCD to ASCII, it is plus 30. Whenever you have a hexadecimal number system has both numbers and characters. So you have to add 30 to number and you have to add 30 plus 7 for a character. That is the only difference in conversion. So whenever you want to do a conversion of the other set of number, that is, say for an example, I want to convert a hexadecimal number system to a decimal number system. How do I do? It is basically hexadecimal is base 16, decimal number system is base 10. I can keep on dividing the base 16 number by 10. Whenever I divide any given number by 10, the remainder is for sure 9 or less than 9. Right? So go on saving those remainder. So remainder will be obviously in decimal number system. Now let's see that particular program. I'll take this example. I'll explain it in the program window itself. I'll just redo a shortcut, not a good practice. But since it is of the same category of program, it's okay. Okay. Now what am I doing? In 9000, I'll take some number. Say for an example, FF. FF, if you convert it into decimal, you should get 255. Okay. So putting purely in decimal form, 020505 is what you are supposed to get. Now how do I do it? I am taking that number. B is loaded with 10. Please note there is no H there. It is decimal number 10. Okay. So B is loaded with decimal number 10. I am dividing the given number FF by 10. So if I divide 255 by 10, 25 is the quotient. Okay. 5 is the remainder. 5 is less than 10. Store it. Take back the original number again, quotient again, 25. Divided by 10. So the remainder is now 5. Quotient is 2. Store it. So for 3-digit number, 2 times of division, the last quotient itself would be less than the 10 number, that is divisor. So you can directly store it. This is the logic. I'll save, translate, build. I'm debugging. So the result is in external memory, x:9000H. Press enter to go into the stack. Let me give the number FF, the same example what I took for explanation. I'll just run. 255, 552. It is always from lower to higher. That's what we store. If you basically write it, it's like 255. Writing it in the order lower byte to higher byte, I'm getting 05, 05 and 02. This is what I'm getting here, the result here. Hope you people had an idea about the code conversion categories of program. So if you practice, if you know the basic conversion procedure that we did in the DSD subject or any other lower semester subjects, the codes from different base systems, so it will be easy for us to write it in terms of a program. There is no big deal. We need to just know the instruction set and that particular logic of conversion, knowing that we can basically write any program to convert from any code to any code. Hoping that you all had understood, we shall continue in the next session where we can highlight on the different approach of program. Thank you so much.